Good day, everyone. We are Cuties, and today we will present our thesis entitled Optimizing Server Allocation for Multi-Method Queuing Service Systems with Dedicated Type and Multi-Class Type Servers. Our study was inspired by a very common real-world problem, waiting in line. Many service systems today operate using multiple service methods simultaneously. For example, in toll plazas, users may either pay through cash or RFID. In supermarkets, customer may choose between cashier lanes or self-checkout counters. Because of these, operators or service providers face an important question. How many service lanes should we allocate to serve each method? Where a server may either accommodate a single method exclusively or accommodate multiple methods simultaneously.
Our study attempts to mathematically capture these kinds of systems. Specifically, we formulate an optimization model that determines the optimal number of service lanes to assign to each method, whether a lane serves a single method exclusively or accommodates multiple methods simultaneously, in order to minimize the average waiting time experienced by users. The model considers the total arrival rate of users, denoted as lambda, the proportion of users for each method p sub I, the service rate of each method mu sub I, and the total number of available service channels capital N. The framework of the model is based on queuing theory, particularly the MM1 model. Using the classical waiting time formula, W, we modify the expression to account for multiple service methods and multiple allocated queues. This reflects the interaction between service capacity and arrival demand. As demand approaches service capacity, congestion increases rapidly and waiting times become significantly larger.
Our model contains two interconnected objective functions. The first objective minimizes the overall average waiting time in the system. And the second objective incorporates user behavior through Wardrop's user equilibrium principle. This principle states that the users naturally choose the queue they perceive to provide the least delay. In other words, if a compatible queue appears faster than another compatible queue, users will gravitate towards that queue until the delay in the system become balanced. So to capture this behavior, the second objective minimizes the disparity of queuing times among the queues. Because the model contains both integer allocation and non-linear waiting time relationships, the resulting formulation becomes a mixed integer non-linear programming problem, or MINLP. So, to ensure realism in our model, we impose several constraints. For example, one constraint here shows that the total number of allocated queues must equal to the fixed available queues given by the user. Also, we impose the stability constraint, which is our constraint number 3. This is important because it ensures that the server's capacity of each queue type exceeds the arrival demand assigned to it. Without these conditions, queues would grow indefinitely and the system would become unstable. In easier terms, the queue will build up since the service is slow compared to the arrival rate. Another important feature of the model is the inclusion of a delay adjustment function. In real-life systems, a queue that accommodates many methods or services may have reduced efficiency when compared to a queue that handles a single method, since they need to switch to different transaction or method types. So to represent this, we introduce the delay adjustment function, which decreases the effective service rate as methods are accommodated into a queue.
We then analyze several mathematical properties of the model. In particular, we established feasibility conditions ensuring that the model has at least one solution that satisfies all imposed constraints. The table presents the necessary and sufficient conditions for both the relaxed and the original mixed integer model. We also showed boundedness and existence of optimal solution for the model, ensuring that the optimization problem is solvable under the specified assumptions. Another interesting result concerns the case of zero mixing penalty. If combining multiple methods in a server causes no efficiency loss, the optimal strategy is to allocate all service channels as fully multi-class queues. Intuitively, if mixing methods carries no disadvantage, then maximum flexibility becomes the most effective allocation strategy.
We conducted numerical simulations and sensitivity analysis using Python, together with optimization solvers such as IPOP and Bondin. The simulations examine how variations in arrival rates, service rates, user proportions, number of queues, and mixing penalties affect the optimal allocation structure. The results revealed several important behaviors. When traffic demand is relatively low, dedicated queues often perform adequately because congestion remains manageable. However, under heavier demand, partially mixed queue systems frequently outperform purely dedicated systems because they provide greater flexibility and better resource utilization. On the other hand, when the efficiency loss from mixing becomes too large, dedicated queues again become preferable.
Overall, the simulations demonstrate that the optimal queue structure depends on balancing flexibility and specialization. Dedicated queues may improve efficiency for a specific method, but they can also waste resources during low demand. On the other hand, multi-class queues improve flexibility, but servicing multiple methods together may reduce efficiency because servers need to switch between different transaction types. In conclusion, our study proposes a generalized optimization framework for queue allocation in multi-method service systems by combining queuing theory, nonlinear optimization, and behavioral equilibrium principles. Beyond toll plazas, the framework may also be applied to hospitals, airports, banks, supermarkets, cloud servers, and other service-oriented systems. Through this study, we hope to demonstrate how mathematical modeling can help design more efficient systems that reduce congestion and improve user experience in daily life.